Oh, we have some questions in the Q&A. So one question is, do we have to specify a distinction between the thoracic cavity and the lungs when explaining the mechanism of ventilation? No. No, that would be too much detail. Another question, when lung pressure equals the atmospheric pressure, does that mean they came into equilibrium and flux/bulk flow stops because there's no difference in pressure? Yeah, I mean, if you had a hypothetical scenario where the lung pressure was the same as the atmospheric pressure, then there would be zero gradient and thus the zero flux. However, that actually never happens because you have some amount of stale air in your lungs. You never get the atmosphere and the lung pressure being the same. Okay, another question. How low is the PO2 of working tissue supposed to be if the blood PO2 is about 40? Oops, let me let someone in. Does that mean if the PO2 of working tissue is 50, then there is no oxygen delivery? So it's always less than 40. So can y'all see these questions? I don't know, because it might be hard if you can't see it. Can y'all like thumbs up if you can see what I'm reading?
No.
No? Okay. Okay. There's a lot of questions here. Oh my goodness. Ah, okay. I wish I could share.
It says that only the host and the co-host can see all the questions.
That's so annoying. Let me see. What do I click answer live? Did that do anything?
Yeah, that worked.
Okay, cool. All right, so now y'all can see what I'm talking about and I'm not just talking words out loud. Okay. So this is how low is the PO2 of working tissue supposed to be? Even that wording just throws me off a little bit. It's not so much what it's supposed to be. The working tissue concentration of oxygen is some number based on how much oxygen gets used. And then the blood PO2 is going to exactly match whatever it is because the blood PO2 comes to equilibrium with whatever it's in contact with. So when the blood goes up to the lungs, that PO2 is going to exactly match that of the lungs. When the blood goes down to working tissue, it's going to match that of the working tissue. So I don't know what is meant by supposed to be. It just kind of is. So then the next question says, does that mean if the PO2 of working tissue is 50, there's no oxygen delivery? So it's always less than 40. No. So if the PO2 of working tissue was 50, then the blood coming from the lungs would be typically about 100. So whether it was 40 or 50, there would still be a gradient for oxygen to go in. And then the blood coming from working tissue, the venous blood going back up, would match whatever the working tissue PO2 was. So in this example, it would be 50. If the working tissue is 40, it would be 40. If it was 30, it would be 30. I'm not sure if that was helpful. But I'll also say some kind of a complicated question like this wouldn't necessarily be asked. What you should know is, yes, if you decrease the PO2 in one area, you should know that that should decrease the gradient and therefore decrease flux. That's about as complicated as it'll get. Next question. Is there a reason why mammalian alveoli cannot match the atmospheric O2? because of the mixing of fresh air plus stale air. The dead airspace takes up some PO2 that could have been fresh air. Yeah, exactly. The reason why it's 100, the PO2 of your lungs is typically 100 and not 160, which is what it is in the atmosphere, is because some of the stale air in your lungs mixes with that fresh 160 air, thus lowering it. Okay, next question. I was hoping you could explain the difference in the pneumothorax, where a collapsed lung occurs and there's a sucking chest wound based on the O2 mechanics we learned. Yeah, so if there's a sucking chest wound, and you have a collapsed lung, all that's reflecting is that the negative pressure between the thoracic cavity and the lungs has been messed up. So you need negative pressure in between the lungs and thoracic cavity to make sure as you expand the cavity, you're also expanding the lungs. And any kind of damage to the thoracic cavity or to the lungs will mess up that little negative pressure relationship that you guys should have seen in lab when you had the little fake diagram and we were pulling down on the diaphragm, and that was actually causing the lungs to move as well. In order for that to happen, you need some negative pressure within the cavity. So yeah. Next question. Ooh, there's a lot of questions. Can you please go over the graph that explains how O2 is saturated differently in cold air? I was unsure how to read and interpret it. Yes, so I will get to that. I'll go over that at the end, just because it's maybe not as important. Would you be able to go over the minute ventilation and the graphs, hemoglobin? Yes, I will go over those graphs. There was a lecture slide with different numbers of yellow balls and asked us to rank the resistances. Was the resistance not related to the number of balls? Why? Yeah, so the resistance was related to the membrane, not the concentration. So the number of balls in that picture were representing the concentration of that molecule. If you change the concentrations, you're not changing resistance. The only way you would change resistance is by changing the amount of openings in the membrane separating the balls to allow them to move. Could you explain why human PO2 can never be as high as bird PO2, those geese at high altitude? Yeah, so birds have a different way of breathing than us. We have tidal breathing, they have unidirectional breathing, because you don't have to know how their breathing works, but basically because they have airflow in just one direction, they're never mixing stale air with fresh air. So they get fresh air coming in, and because they don't have the mixing, they don't have that lowering of the PO2 that we have. And that's the level that you will need to understand. Okay, how does the minute ventilation graph differ between a normal breathing person and a person with asthma, narrow airways? We're going to go over that, but briefly, the actual slope of that graph will change. So the amount of breaths taken per minute will be lower. Can I go over number 7 on my, I'm going to go over my whole sheet. Can you go over? Yes, I will go over the graph. What's the difference between partial pressure and concentration? partial pressure is the concentration of oxygen in whatever space we're talking about. So you can kind of think as partial pressure as being synonymous with concentration, at least in terms of oxygen. Can you clarify which aspects reach equilibrium and which don't? Not sure what that means. So if you ask that question, maybe give me some more detail. I don't know what you mean by that. I asked this question on Piazza, but I'm still confused as to why increasing red blood cell count helps mountain climbers not die when climbing mountains. I understand it helps blood carry more O2, but how does this help if you're getting way less oxygen at mountain altitudes? So if you have more red blood cells, then you'll just be able to increase the amount of oxygen that your blood carries, because 98% of the oxygen in your blood is attached to hemoglobin. So you should just think the more hemoglobin, the more oxygen you'll be able to carry. So yes, even if the PO2 of your blood or your lungs and the atmosphere is less, you'll still get more if you have more red blood cells. Will the test be multiple choice or writing? It will be short answer. Does decreasing flux necessarily mean decreasing the rate of flux? As in, are those the same thing? Flux is a rate. So flux describes rate of movement. So how many molecules are moving over time. So I'd say flux is a rate. Can you give us a guide to the O2 saturation curve questions in general? Maybe? We'll see. Okay. I will try to continue to check that. But if you have questions as I'm going over things, it's also helpful if you say them out loud. Okay, I'm going to share my screen. Maybe. Wait, someone's trying to come in. Okay, share screen. Let's do this one. Okay, so I'll just open this up. All right. There's some more questions. Are we expected to draw diagrams on the exam? Yes, that could happen. So the PO2 of oxygen in your blood is just the PO2 of oxygen not attached to hemoglobin. Yes, the PO2 in your blood is not a reflection of how much is on hemoglobin. It's everything that's outside of hemoglobin. So it's that 1 to 2% outside of hemoglobin. Would we need to memorize the resistances, conductances for bulk flow and molecular diffusion, like memorize the table on bulk flow and diffusion driving forces? No. It would be more like on the exam, you're going to be given some kind of example, like someone said asthma, and the exam will describe how asthma changes something, and you should know, like, oh, that's changing resistance to flow, and because now resistance is higher, that's going to mean less flux. So you'll be given the examples. You don't have to memorize the examples. Okay, so I'm just going to kind of go through these exam notes that I made and hopefully highlight important points that you should know. So the first one is just kind of general. Do you understand the flux equation? So you should know, oops, that's way too thick. Let's see. All right, let's try now. That's still too thick. Okay, yeah, flux. You should know flux is rate of movement. So it is a rate. That's why in the very first worksheet you guys did, it was the slope of the lines. And it equals gradient over resistance. So it's just the rate of movement of some molecule, and it's determined by these two variables. So gradient is the difference in the molecule in two different areas. So it can be the difference in concentration of ions in and out of a cell, or it could be the difference in partial pressure of oxygen between the atmosphere and the lungs, or the alveoli in the blood. And the greater the difference is, the more flux is going to happen, the greater the rate of movement, which is why it's on the numerator. And then resistance is anything that impedes the movement of those molecules. So in general, resistance is going to be maybe a closed membrane. So a membrane that doesn't have any ion channels would be resistance to the movement of ions. Resistance could also be distance. So the longer the distance from the atmosphere to the alveoli, the lower the rate of movement will be. So you should just kind of generally know that relationship, not because you're necessarily going to be tested on it directly, but because to understand everything else we go over below, you're going to have to understand that relationship. Yeah. Was there a question or no?
Yeah, I kind of lost my train of thought though, so I'll raise my hand again when I think of it. Sorry.
Okay, yeah, no problem.
Thank you.
Okay, so can you describe the flux of oxygen, so rate of movement of oxygen from the atmosphere to the lungs? And can you brainstorm ways by changing gradient or resistance you could increase or decrease this flux? So the flux of oxygen from the atmosphere to the lungs, what you should know about that is number one, that it is a bulk flow. And so bulk flow and diffusion are the two different types of flux we talked about. Diffusion is of particular molecules, whereas bulk flow is of lots of stuff all at once. So we move all air into our lungs with everything in it, not just oxygen molecules in particular. So what you should know about bulk flow and the fact that that's the movement happening from atmosphere to lungs is that it's non-specific and it's quicker than diffusion. So the reason why we don't use diffusion is because it would be too slow to get enough oxygen from the atmosphere into the alveoli. The distance from the alveoli to the atmosphere is too large, so we wouldn't get enough oxygen to support life. So you can kind of think about kind of normal baseline sea level conditions as being the I can't write, the total atmospheric pressure is around 760 millimeters of mercury. I'm going to erase that and start over. I don't know why this is not writing really well. It seems like the more people who join the Zoom, the slower my computer works. Okay, so in sea level normal conditions, that is the total pressure, air pressure in atmosphere. And around 21% of that air is oxygen. So one thing you should be able to do is, given like a total air pressure, you should then be able to calculate what would be the partial pressure of oxygen if it's 21%. So we would have to give you the 21%. But if you multiplied 760 times 0.21, you would get that the partial pressure of oxygen is around 160. So this is how much oxygen is in the atmosphere. And then typically what we see is going from the atmosphere to the lungs. Once you get to the alveoli in the lungs, the pressure is around 100 millimeters of mercury. And like I said at the beginning, the reason for that drop in partial pressure is just because once that air gets into the lungs, it mixes with some of the air that's already in your lungs, and some of that air has a really low partial pressure. So when it mixes with it, you end up with a bit of a lower partial pressure. So what you should be able to do is say, like I said, can you brainstorm ways of, if you change the gradient or resistance, could you increase or decrease this flux? So for example, let's say that we change the atmospheric pressure by going to conditions where we are now at a different elevation. So let's say we're at a higher elevation. And let's say that we're at maybe, I don't know, let's go to an example from one that he talked about. Let me see. Can y'all still see my screen? Or it's like if I click to a different tab, can y'all see it? Yes.
Yes.
Cool. Okay. So this question here is a good example of something you should be able to do on the exam. So normal conditions, we have 760 and 160 for oxygen. But what about in these other conditions? So let's just go over like the Tahoma case. So let's say he gives you, you're at a new location and it's 14,000 feet above sea level. Can you then calculate what the new partial pressure of oxygen will be? And then on top of that, can you determine how that's going to change the amount of oxygen delivered to your body? So let's just go over like the Tahoma case. So if Tahoma is at 14,000 feet, you will have to be given some kind of graph like the one shown here. And you can see at about 14,000 feet, we're at about 0.5 the amount of air pressure. So what you would do in that case is just take the normal amount of oxygen, which either you'll be given enough information like this to calculate, or it'll just be given to you. And then based on the new elevation and what the graph says, you should be able to calculate what the new partial pressure of oxygen in the atmosphere will be. So let's say it's Tahoma. So you would multiply whatever the normal partial pressure is of oxygen times, in this case, 0.5. And you would get that the new atmosphere concentration would be 80. Oops. So if normally we have 160, and by the time it gets to the lungs, we have about 100. Now we're saying we start in the atmosphere with 80. You can think about how much would get to the alveoli, given that some of it is going to mix with the stale air in your lungs. So you could even kind of set up like a little proportion and say that normally it's 100 and 160, and now it's 80. Oops. So how much, what would the partial pressure of your alveoli be? And so I just calculate that as 80 times 100 divided by 160. So it'd be like 50. So going from the atmosphere to the lungs is now 80 to 50. So you should be able to do that calculation, and then you should be able to interpret what is the effect of that going to be on oxygen transport. Yeah, is there a question?
Yeah, can you hear me fine?
Yeah.
Okay, good. So how did you calculate the 50, which is the pressure in the lungs? Did you just look at the ratio of 100 to 160 and then
Yes.
use that? Okay.
Yeah. Yeah, so then what is the effect of that going to be? So I think kind of the initial thought that you should have and what makes sense is that you've said, well, now there's a lower concentration of oxygen in the alveoli. And so if I'm thinking about oxygen going from the alveoli to the blood and the rest of the body, I've decreased the gradient, right? Before, when you think about, like, here's my lungs. Oops. And I have some blood coming in, and then it gets oxygenated, and then it comes out. The blood coming in is usually around 40 millimeters of mercury. And normally we have 100 millimeters of mercury in the lungs. So by changing this number to 50, what we've done is decrease the gradient, right? So flux would be normally the gradient of 100 minus 40 over whatever the resistance is. And now it's, oops, 50 minus 40. So that gradient, that difference in concentration, has greatly decreased. Yeah, question?
Yeah, so would we be given like the 40 millimeters of mercury, or could we just say that, like, since the pressure is decreasing to 50, that the flux would decrease too?
Yes, yeah. All you would have to know is if you decrease the concentration in the lungs, that should decrease flux. Right?
Okay, thank you.
Yeah. And then remember, so for the blood coming out of the lungs, it's just going to equilibrate with whatever the concentration is in the lungs. So in this new case, it would be 50 millimeters of mercury. So your first answer to this question is going to be, okay, in this case, I've made some kind of change to the gradient, and because of that, I've decreased the flux, right? So you might have to do some math, and your first answer is going to be using flux reasoning. We've decreased the gradient. But that's not the end of your answer. So if you're asked the question of what is the effect of this going to be on oxygen transport, you can't just say decreased flux, so bad. One big key point that he really emphasized in class, and it's going to come up on the exam, is that just because this is lower doesn't necessarily mean that oxygen transport is going to be affected. Why? Because of that oxygen hemoglobin graph. So let me see, I can find that here. Oop, there. Let's see. This one. There we go. Ah, I don't know why it's turning black. Yay, okay. Okay, so we found that if you go to higher elevations and you decrease the amount of oxygen, blah, 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 you decrease the amount of PO2 in your alveoli, which is going to decrease flux to your blood, but you're still going to get the situation where your blood's going to equilibrate with your lungs. So yeah, now your blood doesn't have 100 millimeters of mercury. It has 50. But is that going to actually affect how much oxygen you get to your tissue? And it all has to do with this graph here, because that partial pressure concentration being 50 only has an effect based on this graph. So this graph shows you how much hemoglobin is saturated given what the partial pressures of oxygen are in the blood. So normally the partial pressure is around 100, and it's nearly, the hemoglobin molecules are nearly saturated with oxygen. So they have a ton of oxygen. Now we've gotten down to 50. So maybe like right here. And the key is that, yeah, it's less. It's definitely not 100%, but there's still a pretty high saturation of oxygen for hemoglobin. So hemoglobin's still going to be able to store a ton of oxygen, even at this new partial pressure of oxygen that's significantly lower. So the point is, when you answer a question like this, you need to go and look at this graph to decide whether it's going to be a big deal or not. If you change the partial pressure and it's anywhere from like maybe 40 to 100 and above, your hemoglobin's pretty saturated at all of those partial pressures. So it's really not that big of a deal if you change the partial pressure within that area. It starts to become a big deal if you change the partial pressure down to below 40, because then you start to get hemoglobin to be not as saturated, so you're carrying much less oxygen in your blood. Yeah. So for number 2, the main things I want you to focus on is, number 1, can you calculate changes in partial pressure given changes in an initial pressure concentration due to elevation? And then 2, can you tell me how it'll change flux? And then 3, based on the hemoglobin graph, can you tell me if that's really going to decrease oxygen delivery or not? And if hemoglobin is still pretty saturated, then it's not going to decrease oxygen delivery very much. Does that make sense? Any questions on that? Yeah.
Do you have any like example problems or practice problems for this specific question that we could use to practice? Or
Yeah, so I would say, like, I just went over the example of Tahoma, but a really good practice that you could do is the Everest case. So you should expect to get some, some change. Can you calculate the new concentrations based on that? So use the Everest example where I think it's like, now you're at like 30,000 feet. What would be the new concentration of oxygen in the atmosphere, in the alveoli, and then in the blood? And based on what it is in the blood, is it actually going to affect delivery or not?
thank you.
You're welcome. Yeah, another question?
So I'm just slightly confused on the concept of being at 14,000 feet. Like when you go up there, it's obviously harder to breathe, but you're getting the same amount of oxygen. Is that what you're kind of saying?
Yeah, I'm saying it's actually not that big of a deal to be at the top of Tahoma.
Okay.
Now, if y'all go tonight and say, I'm going to do the Everest example as my practice, you'll find that that's not the case. But you should use the graph and prove it to yourself. Yeah, question?
Hi, so for the altitude question as well, does the oxygen levels in the blood remain constant? It's just the breathing that becomes harder? The driving force lowers?
Yeah, so as you change the elevation, you're going to change the partial pressure that enters the lungs and then therefore the blood. So you are going to change the concentration. But this concentration, I mean, as long as it's like above 40, it's not going to affect how much oxygen is in total in your blood, because hemoglobin is holding 98% of the oxygen in your blood. So
Okay.
most of the oxygen is on hemoglobin. And as long as hemoglobin is like, 80% or above saturated, then you really haven't decreased your oxygen that much, right?
Mm-hmm. So you just have to breathe more for the same amount of oxygen, pretty much. That's why driving force is decreased.
Yeah, I think that for those changes, I wouldn't even expect you to really have to breathe that much more. it'd be pretty low to negligible.
Okay, thank you.
You're welcome. Next question.
Yeah, so then I don't know if this is correct, but from my own understanding, like you can start to feel the effects of altitude sickness at around like 9,000 feet in elevation. And so if the hemoglobin is still mostly saturated at that elevation level, what explains the like symptoms of altitude sickness? Or is that just a variance from person to person?
Yeah, it varies from person to person, and I don't know the details of why you get altitude sickness, and if it has to do with if it's a direct readout of you're not getting enough oxygen.
Okay.
But yeah, in general, you should come back to this graph when you're trying to decide whether the amount of oxygen in your blood has really decreased or not. And if you're in this kind of top flat area, you're not really decreasing the total amount of oxygen in your blood that much, because most of it is in hemoglobin, and hemoglobin's saturated. Okay, 3 says, can you describe the flux of oxygen from the alveoli to the blood? So the big difference with this one compared to number 2 is that flux is now diffusion. Oops. So because the alveoli is so close to the blood, they're literally like 2 cells apart. That distance is really low, so the resistance is pretty low, and you can get movement of oxygen via diffusion, even though diffusion is slower. Can you brainstorm ways by changing gradient or resistance you could increase or decrease this flux? Yeah, so the main things that you should know for this is whatever the concentration of oxygen is in the alveoli, that's going to be a direct readout of what the concentration of the blood is going to be, because they come to equilibrium. So one question you could think of is, let's say you get an example of changing the elevation, changing the atmospheric concentration of oxygen. How would that affect flux from alveoli to blood? And it's going to be kind of similar to how it would affect the flux of oxygen from the atmosphere to the lungs, right? Because they come into equilibrium, if you lower whatever the concentration is for the alveoli, because you lowered it in the atmosphere, you'll also lower it for the blood. So it's kind of the same question as the last one. And again, whether that has big consequences depends on where you end up on that hemoglobin graph. Okay, let's see. One way I could think of is like, yeah, changing gradient. The only way you could change the gradient is by changing the alveoli partial pressure. And the only way to change the alveoli partial pressure would be changing the amount of oxygen coming in. So it would have to start with some kind of change in the atmosphere. Changing resistance, it could look like, I don't know, maybe there's some kind of disease that thickens the walls of the blood near the alveoli. So the capillaries now have some kind of thickness to them that would increase the resistance and then decrease the flux. Yeah. I think the important thing that you'll need to know for the test is realizing that whatever the alveoli partial pressure is, that reflects what the blood partial pressure will be. Okay, can you describe the role of hemoglobin in oxygen transport? So big picture, you should know hemoglobin is the protein that's in the red blood cells that binds to oxygen. And its big role is that it increases the total amount of oxygen that can be transported in the blood. So regardless of what necessarily the partial pressure is, because you have this hemoglobin molecule, you can end up storing a lot more oxygen in your blood because it doesn't take part in the PO2. So if you have a PO2 in your lungs of, let's say 60, then in your plasma, the highest that you can get your PO2 in your blood is 60. But if you increase the amount of hemoglobin molecules in your blood, you can take some of those molecules from the plasma and store them in the hemoglobin. So then you can get more and more oxygen coming in. And even though that partial pressure never changes, the more hemoglobin you have around, the more oxygen you can store. So one thing I kind of wanted to go over with this is this question. So understanding this will be something that will help you for the test. So the question says, you ventilate strongly and increase your lung PO2 to 140 millimeters of mercury from 100. So this is an example going in the opposite direction. I've been doing a bunch of decreasing concentration examples. Now it says your blood will now store a lot more O2. At the lung, your blood plasma will ideally reach 140 millimeters of mercury PO2, which is more O2 than just 100. B, a bit more O2. While A is true, the vast majority of blood oxygen is bound to hemoglobin, and hemoglobin is already near saturated at 100 millimeters of mercury PO2. C, not enough information. The graph only goes to 100, so we don't know what happens at 140. So what this problem is saying is normally we're at this 100, and now we're jumping to 140. And even though we've increased the concentration in the plasma, it doesn't necessarily matter because at 100 and everything above it, we've already plateaued our hemoglobin. And if all of our oxygen, or 98% of it, is stored in hemoglobin, then even if you increase it past that 100, all of your hemoglobin are all saturated. So you're not going to increase the amount of oxygen by that much. So B would be the answer. Okay, this is another one that's a good example. So it said, you don't eat enough iron, so you produce fewer red blood cells. Your blood will now store A, less O2, your hemoglobin will be nearly saturated with O2, but there's less hemoglobin to saturate. The same O2, the number of red blood cells won't impact the partial pressure of oxygen, so you'll still have O2 delivered from high partial pressure to low partial pressure. Or C, the same O2, any millimeters of mercury above 80 is enough to mostly saturate the hemoglobin with O2. So if you produce fewer red blood cells, you will have less oxygen. So because most of your oxygen is stored in hemoglobin, if you decrease the amount of hemoglobin, then you'll have overall less oxygen in your blood. And it is true that it doesn't affect the partial pressure, but it will still affect the overall amount of oxygen in your blood. Okay, can you read the oxygen hemoglobin dissociation curve and explain and predict the effect of changes to it? So different shapes, left or right shift. So go. So this is the oxygen dissociation curve, and changes in shapes would affect kind of, would demonstrate whether or not there was more or less cooperativity between the binding of oxygen molecules. So if instead of this shape, let me just draw it, this kind of S-shaped curve, you had more of a linear line, that would tell you that as you increased the amount of oxygen concentration, the binding increased the same. So on the y-axis, that tells you saturation or amount of oxygen molecules bound to hemoglobin. And the bottom is the partial pressure or the concentration. So if as you increase the concentration, the saturation increased by the same amount, that would mean that as one molecule bound, it didn't affect the likelihood of another molecule binding. If you get the curve shifting to be more of an S shape, that's showing a really high amount of cooperativity. It means that as you increase the concentration of oxygen, that makes it extremely more likely that more molecules will bind. And that's why you get this very stark upward shift to the curve. Other ways you could see the graph change is you could see it shifting from left to right. So if you saw a leftward shift, that would mean a higher affinity of hemoglobin to oxygen. So it's saying at very low concentrations of oxygen, you're now getting a high amount of binding. If you saw a rightward shift, that would be a lower affinity hemoglobin for oxygen, meaning that it would take very high amounts of oxygen to get a bunch of it binding to hemoglobin. So the big thing with the oxygen hemoglobin curve is going to be kind of like I already said, but I'm going to emphasize it because I think it's important, is connecting the curve to the outcome of changes to these two things. So if you change the amount of the partial pressure of oxygen, what is the effect going to be on how much oxygen is stored in hemoglobin? That's kind of the main things you should know about the curve. Yeah, question?
Can you go over the example from the lecture slide with the cold air and this specific graph, how the saturation curve shifted when the temperature was colder, and how to kind of interpret that one?
Yeah. So this is an example from lecture that showed that in colder temperatures, you got kind of a left shift to the oxygen dissociation curve for hemoglobin, which says that at lower concentrations of oxygen, hemoglobin is binding to oxygen with higher affinity. So why does that matter? Well, that says that if an animal is in really cold temperatures, they might be better, more efficient at getting oxygen via hemoglobin than they are at hotter temperatures. So the idea was that maybe the bar-headed geese can fly at really high elevations with no problem, because at those high elevations, their hemoglobin is actually working better because it's colder air. Now that's just a hypothesis, but that's kind of what the idea is. So in general, if you see the curve shift left, you're thinking hemoglobin is binding to oxygen better. It has a higher affinity. And that's really good for getting oxygen in areas where there's not much oxygen. It can be maybe a little bad if you're on the other end of that and you're trying to actually release oxygen from hemoglobin to your working tissue. In that case, you want hemoglobin to actually have a lower affinity. And that's why, so like in this curve, if the working tissue had a, I don't know, a concentration of 20, at that point, hemoglobin would still be holding on to quite a bit of the oxygen, which wouldn't be ideal for actually delivering it to tissue. Whereas if you look at the normal graph, at 20, if you got your working tissue down to 20 millimeters of mercury, your hemoglobin would be very good at releasing oxygen and replenishing that lowered amount. Okay, can you compare and contrast the flux of oxygen from the atmosphere to lungs versus alveoli to blood? Yeah, question?
I was wondering if you could go over those graphs you drew. I think it was for 5, those with the blue lines,
Yeah,
blue curves, like what the shift means regarding hemoglobin and everything.
yeah. Let me try redrawing it. So in this graph, we have saturation on the y-axis, which is basically how many oxygen molecules are bound to hemoglobin. So if it's 100% saturated, all of your hemoglobin have all of its binding sites taken up by oxygen. And then on the x-axis, you have amount of oxygen in PO2. So the normal curve looks something like this, which says that, I think this is usually around like 40-ish. And then here it'll be like 100. When the concentration of oxygen is around 100 in your blood, then basically all of your hemoglobin is full of oxygen, which means the blood near your lungs is getting as much oxygen as possible because hemoglobin is completely saturated. And then if you get down to working tissue that is, maybe you're exercising and it's super low, and it has a concentration of 20, then at that point, your hemoglobin is going to be maybe super low. It's not going to have a very high saturation of oxygen, which means it's going to give up a lot of oxygen at those concentrations. So what you have is in areas where you want hemoglobin to be really grabby with oxygen, it will bind to a lot of oxygen. And then in areas where you want hemoglobin to be not very grabby and to be giving up oxygen, it'll give up oxygen at low concentrations. Now, what would different shapes of the curve mean? So if you had a rightward shift to the curve, that would mean that your hemoglobin molecule has a lower affinity for oxygen, meaning that as you increase the concentration of oxygen, normally it would be all of a sudden binding a bunch of oxygen, but this one takes more oxygen being around in order to bind it in the same amounts. So it's not as grabby with oxygen, if that makes sense. If you had a leftward shift, that's the opposite. That's saying that's a hemoglobin molecule that has a really high affinity for oxygen because you increase the oxygen concentrations just a little bit. And even at very low concentrations of oxygen, it's super grabby. It's already increasing the amount of oxygen that it binds, and it becomes saturated at very low concentrations, whereas this
Okay.
low affinity would take more to become saturated. Does that make sense?
Yeah. Yeah. Oh yeah. I had a question. Thank you. So does the affinity have to do with like a defect in the hemoglobin, or like why is it more or less grabby with oxygen?
Yeah, so you could get mutations on the hemoglobin protein that make it the binding site less of a low energy state for oxygen. Yeah.
So normally it's in the middle, but a higher or lower affinity would be caused by mutation.
Yeah,
Okay. Thank you.
you're welcome. Okay, can you compare and contrast the flux of oxygen from atmosphere to lungs versus alveoli to the blood? How and why are they different? This is kind of a, I think, in my opinion, more easy, straightforward thing that you have to know, which is just that the first one is bulk flow and the second one is diffusion. What are the big differences between those two? Bulk flow is quicker, diffusion is slower. An application of that that you might see, not this exact example, but something kind of getting along the same thing, is the example he went over in his review, which is like if you had a worm that was 2 cells in diameter, would that worm need to get oxygen via bulk flow? And the answer would be no, because it's only 2 cells in thickness, it can just do diffusion. So what does that mean for you? It means that you should have in your head going into this test that if you get indicated that the distance the molecule of oxygen needs to travel is really low, then diffusion is good. And if the distance is really large, then diffusion is no longer going to work. So all I'm saying is on the test, have that relationship in your head. Increasing, if you're told an increase or decrease in distance, you should know how that will affect whether you want to use bulk flow or diffusion, or how well diffusion will work. Number 7, can you describe what is meant by mammalian tidal breathing and what is minute ventilation? So tidal breathing is just inhaling and exhaling breathing that isn't unidirectional. So instead of having air just move in one direction the entire time, air goes in and out, back and forth, right? So in birds, when they like inhale air, that air travels one path and it never goes back in the other direction. Whereas mammals, they have one little tube and they breathe out and they breathe in, back and forth through that same tube. So that's what tidal breathing is. And you should be prepared for seeing a graph of tidal breathing. Maybe look something like this. And then you should, let's see, what did it say? Can you describe how changes to resistance or gradient would affect a graph of tidal breathing? And also, what is minute ventilation? Okay, so let's say you're given a graph like this, and it's like 0.5, 1, 1.5, 2, and say and this could be liters. So first, what is minute ventilation? Minute ventilation is going to be volume of air inhaled or exhaled per minute. And you should be able to tell me what the minute ventilation is given one of these graphs. So how can you go from this graph to minute ventilation? Well, minute ventilation is just respiration rate times tidal volume. So respiration rate is breaths. Oops, I don't know why this is writing so bad. Breaths per minute. And then tidal volume is volume per minute. I mean, sorry, volume per breath. So how do you get the respiration rate from this graph? Well, you can see that every time this curve repeats, that's one breath. So wherever you want to start to measure it, you can. So we can say like here to here, or you could have measured here to here. That's one breath. This is one breath. Wherever you want to start and end is fine. Go here, back to here, and say that's one, whatever. I think this one here is the easiest. So you can see that you have about 1 breath per 5 seconds. So if you have 1 breath per 5 seconds, how many would you have in 1 minute? Well, there's 60 seconds per minute. So 5 times 12 is 60. So you have about 12 breaths per minute. So that would be your respiration rate. So your first step to calculating minute ventilation is find out what the respiration rate is by using the graph to find what is 1 full breath, and then looking at the time that it takes, and then from that time figuring out what would be the total number in a minute. And then you get the tidal volume, which is the volume per breath. So that would just be whatever this volume here is. So in this case, it's 0.5 liters. You do 12 times 0.5, and that would be your minute ventilation. So as he said in his review, he's not going to have you actually do the calculations. You'll just have to write out the equations. So in order to do this, you need to know that minute ventilation equals respiration rate times tidal volume in order to get your final equation. Okay, what else might you see with these graphs? In addition to having to calculate minute ventilation, you should be able to explain how minute ventilation might change given different examples. So 2 examples that I got from his PowerPoints were decreased contractions of the diaphragm, and then asthma. So maybe I'll just go and find those so y'all can know what I'm talking about. Yeah. So 2 examples he gave here were like, okay, how would the graph change if you had weak breathing muscles? And then another one would be asthma. So weak breathing muscles or collapsed lung or pulmonary fibrosis, which is when the lungs, they kind of harden so they can't move as much. All of these decrease the volume of air that can get into your lungs. And so what the change would look like is you're given a graph. You're not going to change the amount of breaths per minute, but when those breaths are taken, they should have a lower volume. So I draw something like this. If you were told less volume by weakened diaphragm or weakened breathing muscles, I would draw something like that. And then maybe you have to calculate the new minute ventilation. So your rate, your respiration rate would be the same, but you decreased that tidal volume, thus decreasing the overall minute ventilation. Another example you might see is not changes in the total volume, but changes to how big the airways are. And you should think of those as being resistant changes. And so that's not necessarily going to change the volume, but it's going to result in slower changes in volume. So what that could look like is, instead of changing at this rate here, it's going to be the same volume, but it takes longer. So the total number of breaths per minute has decreased, even if that volume is the same as the original graph. So in general, you should think resistance changes. I'm going to draw a slower respiration rate, but not necessarily change the volume. And then changes to the amount of volume in the lungs, that's when you would change the tidal volume and the actual height of those bumps. So be prepared for changes to the gradient or the volume or to the resistance, and then know how to draw your new graph and calculate new minute inhalation. Okay, the last thing is phospholipid bilayers present resistance to flux of which molecules, and how can those molecules get across the membrane? So this is also going to be, I think, one of the more straightforward type of questions that you get. So let's say that you have a membrane, and on one side you have O2, potassium, CO2, and glucose. And you have a high concentration of those molecules on one side and a low concentration on the other side. What will the flux of each of those molecules be across the membrane? So you should know that it is small, nonpolar molecules that can go directly through the membrane, and anything that is big or polar cannot. So oxygen and CO2 will be able to move directly across the membrane. Potassium and glucose will not. Glucose because it is too big, and potassium because it has a charge. So it actually should be small, uncharged molecules can go directly across. So if you see a molecule that is large, polar, or charged, cannot get across, small, uncharged, nonpolar can. So that's a pretty straightforward question. And now that I get to the end, there is one more thing that I want to go over that I think will show up, which is the Le Chatelier's principle. So Le Chatelier's principle is the idea that if you have some kind of chemical equation, we can just do the one we talked about. If you make changes to the amount of any of these molecules, then the response is to go against that change. So if I increase the concentration of oxygen, then this chemical reaction is going to shift to decrease the amount of oxygen molecules. And how will it do that? By having hemoglobin bind to more oxygen. So any kind of increases on this side will shift the chemical reaction towards the other side. And if instead we had a bunch of bound hemoglobin, that would actually shift the chemical equilibrium the other way to let go of oxygen. So what you should expect is you might be given a chemical equation and then be told some kind of random change to it, and then be able to predict the consequences of it. So you should think if you increase one side, you're going to move to the other. And yeah, that is all I wanted to go over that you should specifically know, but I'm happy to answer any questions that you have. Yeah, question.
Hi, could I please see what you wrote for 9 again? The whole thing with the phospholipid bilayer.
Yeah.
So you were saying that, like, what goes through again? You said nonpolar goes through?
Yeah, small, uncharged, and
Uncharged.
nonpolar. And really the ones you should know, if you just want to know, it's oxygen and CO2.
And as far as like the type of questions we would be asked, it would be like what can go through. That's all we need to know for this, pretty much.
Yeah, or I'll give you an example. I'll say there's sodium over here and there's a membrane. Can sodium get across? And you'd be like, no, sodium has a charge.
Okay, gotcha. Thank you.
You're welcome. Yeah, question?
I was wondering if you could show us like another example of like it was the minute breathing calculations.
Yeah. So it's minute ventilation.
Yeah.
So minute ventilation is going to be respiration rate times tidal volume. Let's say you have something that looks like this. And let's go with, this is 2, 4, 6, 8 liters. And then this is time. Let's say it's let's say this is 10 seconds, 20, 40. Okay, so you'll be given some kind of graph like this. You won't be given this equation. You just have to know it. But it'll say like, what is the minute ventilation for this breathing? So the respiration rate is the amount of breaths per minute. And actually, I don't like this because I kind of made it too easy by doing 60 seconds. So pretend this isn't here. You'll have to like calculate it. Let's see if I can just, okay. Oh my gosh. I'm just gonna start over. Oh my gosh. I don't know what is happening. I'm gonna do a new one. Okay. Let's say this. So we have to do respiration rate times tidal volume. Do minute ventilation. So respiration rate is number of breaths per minute. So in this case, I'm going to say, let's do, actually, yeah, here to here. So you would have to get what that distance is, and that would tell you the time it takes to do one breath. But it might be easier to, in this case, just go to like how many total breaths have happened in like 30 seconds. So here it's like 1, 2, 3, 4, 5. And let's say this is harder than it's going to be on the test. So let's ignore this part. Let's just say it ended there. Then it would be 1, 2, 3, 4, 5 per 30 seconds. So for 60 seconds, it would be 10. So my respiration rate is 10. So it's not going to be where it's hard to tell, but just you can choose 1 breath or 2 breaths and then see, okay, I have 2 breaths per this amount of time, or I have 1 breath per this amount of time, and then multiply that amount of time to get 60 seconds to find out how many breaths per minute. And then to get the tidal volume, that's the total volume in 1 breath. So it would be like, what is the total amount in a single increase? So here it looks like, oh my gosh, I don't know. Why is this happening? I keep clicking things I don't mean to. No, okay, go away. Oh my gosh. Okay, so here it looks like 1 breath is 4 liters. Ta-da, then that would be your answer. The minute ventilation would be 10 times 4. And you wouldn't have to calculate it because he's saying no calculators.
All right, thank you.
You're welcome. So someone asked, how long will his test be? Typically, so I'm not quite sure what the final will be, but typically it's about 6 questions long. What do the 2 lines on slide 23 of lecture 4 mean? What are they comparing? And y'all can keep asking questions out loud if you have them as I go through these written ones. Do we need to know membrane transporters for exam 1? No, you just need to know what molecules need transporters and which don't. So small, nonpolar, uncharged do not need channels or transporters, and large or charged or polar do. Yeah, question? Someone's raised their hand.
Hi, could I see the tidal breathing graph one more time?
Yes, you can.
Thank you. So there's 5 breaths in 30 seconds too. Is that another way you can look at it?
Yes, yeah. It's technically looks like it's like 5 and 5.3 because of the way I drew it at the beginning. But it's not gonna
Oh, okay.
it's not gonna
I
be
see
that
what you mean.
ambiguous on the test.
Okay,
It'll be more like straightforward.
gotcha. Okay, thank you.
You're welcome. Oh my gosh. 23. Oh wait. So the 2 lines shown here are comparing how grabby hemoglobin is for oxygen. So the oxygen hemoglobin dissociation curve shows how saturated hemoglobin is with oxygen at different concentrations. And this is saying that at cooler temperatures, hemoglobin grabs onto oxygen way easier. So it's very grabby with oxygen compared to at hotter temperatures where it's not quite as grabby, meaning like if you look at a concentration of 30, at a concentration of 30 and 44 degrees Celsius, then it's only about 5% saturated. Whereas for the 37 degrees Celsius temperature at a concentration of 30, it's kind of near more like 17% saturated. So it's grabbing onto way more oxygen molecules in the cold than it is in the hot. So can we interpret high O2 saturation as a sign that flux is still successfully happening, isn't too impacted? Yeah, so yeah, kind of going back to this curve and how you should be interpreting it on the test is if there is high saturation of O2 on hemoglobin, then oxygen delivery is still happening very successfully. Is the amount of oxygen released to the working tissue depending on the partial pressure of the blood or the working tissue? Which one do we look at? So the amount of oxygen released into the working tissue depends on how much oxygen is in the blood. And how much oxygen is in the blood is determined by the concentration and also hemoglobin. So as long as your alveoli has a concentration from like 60 and above, then that's a great concentration for hemoglobin to be completely saturated with oxygen, and there's just a ton of oxygen in your blood. If your alveoli dips down to a concentration of, say, like 40 or below, now you're starting to get your hemoglobin a lot less saturated with oxygen. And because most of the oxygen in your blood is on hemoglobin, now it's a problem. So not a problem, more of a problem. And then it's kind of funny because down here, this is actually the concentrations near your working tissue. So now down here, hemoglobin is very unsaturated. It's letting go of all of its oxygen. Here, hemoglobin's grabbing onto oxygen. Here, it's letting it go. So at the working tissue, hemoglobin's really good at donating oxygen to the working tissue. Whereas near the lungs, hemoglobin's really good at not donating it and kind of holding on to it at these higher partial pressures. Is there an equation for calculating the partial pressure differences at different elevations? Or do we take the O2% and multiply it by 760 and go from there? Yeah, so yeah, there isn't really an equation, but there is a process that you would do to go. So you would have to be given like the normal amount, either like the normal total pressure of the air, and then be given maybe like a new elevation. So let's say it's like 10,000 feet. And then you would have to be given, well, what is the difference in the pressure at sea level versus 10,000 feet? So let's say at 10,000 feet, and I'm just making this up, it's like 0.4, the amount of pressure. So then you would have to, if it asked you for what's the total difference in pressure of the atmosphere, then you would just do 760 times 0.4. If it asked what's the difference in oxygen partial pressure, well, then it would be 160 times 0.4. So you would have to be given these numbers and this and this, but you would have to know that you take this number and multiply it by 0.4 to get the new PO2. And then from there, what you're going to do is look at that PO2, see how it's going to impact the gradient, and then look at the hemoglobin curve and see whether it's really affecting how saturated hemoglobin is or not. If it's within that top range, you're going to say, yeah, it's not really that big of a difference. But if it's kind of below where it starts to dip down, then you're going to say, oh, that change was actually kind of a big deal because now hemoglobin is not very saturated. So we really impacted how much oxygen we're delivering to the body. Someone asked, why would decreasing the concentration in the lungs decrease oxygen flux? If atmosphere is the same, wouldn't the gradient have increasing flux? So, well, it depends on where you're talking about. So if you decrease the concentration in the lungs, then you would, so let's just draw a big atmosphere to lungs to blood. So if you usually have a concentration of 100, let's say you change it to 50, then you are decreasing the gradient from the lungs to the blood. But I think you're saying if the atmosphere is increased, wouldn't that increase flux? Well, this decrease happened because you decreased the atmosphere. If you somehow held the atmosphere concentration constant and just decreased the lungs, then yeah, you would increase that gradient, but that would never happen. The only way you're going to see this decrease is if you've decreased the atmosphere. That's the only way I could imagine it happening. So like on the test, examples that you'll get is maybe decreasing the gradient by changing the atmosphere elevation, or maybe like increasing, I don't know, the percentage of oxygen in the atmosphere. I don't know. The exam will present you with some kind of change, either increasing or decreasing. And whatever you do to the atmosphere, whether you increase it or decrease it, that's going to result in the same change to the lungs and the same change to the blood, because remember, the blood is just a direct readout of whatever the lungs is. So if you change the lungs from 100 to 50, the blood will also go to 50. Now, whether that affects how much oxygen you deliver depends on the hemoglobin graph. Is the lab canceled this week? Yes. There's no lab this week. So the PO2 of working tissue would equilibrate with the PO2 of the blood. Yes. No matter what. No matter what. Whether there was a lot of hemoglobin or not. Yes. Yeah, so the PO2 of the blood near working tissue is whatever the working tissue is. The PO2 of the blood near the lungs is whatever the lungs PO2 is. And a big point that you should know is that changing the amount of hemoglobin or the amount of red blood cells is not going to change the PO2. And I think that's something that confuses a lot of people, including me the first time I learned it. And it's important for the test. So like if I tell you your lungs are at a PO2 of 50 and you have person A that has, I don't know, 100 hemoglobin molecules in their blood, and you have person B that has 10,000 hemoglobin molecules in their blood, what will be the PO2 of each of those people? For both of them, it should be 50 still. So the amount of red blood cells, the amount of hemoglobin does not impact PO2. It does impact how much total oxygen is in the blood, but it doesn't impact PO2. Yeah, other questions? Let's see what else. If there's anything else I should say.
Oh, hello. I had a question. So you said that the hemoglobin only impacts total blood oxygen, but not PO2, right?
Yes.
So you said both of them would have a PO2 of 50,
Yes.
even if person B has more hemoglobin.
Yeah.
Gotcha. And then I had another question about the Geese curve.
Yeah.
So why does the curve being more linear instead of S-shaped help the ducks survive a low oxygen environment? Is that something we should know? Like, because their curve is it's not really as much of a curve, it's more linear.
Yeah, that part of the curve would not help it. And you don't need to know, but as a fun
Okay.
fact, no, it wouldn't help.
It wouldn't help.
No.
Okay.
Yeah.
All right, thank you.
Yeah. Yeah, I guess I would say a really good like practice that I would recommend for y'all to do is, so if you go back to that slide that had like sea level, Tahoma, Everest, try out those examples, or maybe make your own example of some random elevation. See if you can calculate the new PO2 of oxygen in the atmosphere, and then see if you can calculate what the new lung and blood PO2 will be. And then tell me, will that affect oxygen transport by looking at the hemoglobin graph? I think that would be a good practice for y'all to do. And then another practice I would suggest is for like minute ventilation. Maybe draw your own graph and draw one where it got a lot bigger, or it got a lot more frequent, or it got a lot smaller. And then see if you can calculate what the difference in minute ventilation would be. Yeah. Yeah, Le Chatelier's principle, that's another one you should know. And also be prepared for maybe a new chemical equation that you've never seen before. But still, it's some kind of chemical equation, and they're changing the amounts on either side. And you should say, okay, if you're increasing one side, that's going to push it the other way, etc. Compare and contrast bulk flow and diffusion, and be able to tell me when you can do each based on whether the resistance and distance is long or not. Yeah, I think those are kind of the main things to focus on, but I'm happy to answer any other questions or more questions about the same stuff. Okay, some more questions. So the blood PO2 will become what the PO2 of the working tissue is. Yeah, and let me see, there might be a picture of that. Let me see if it's this one. I thought if you had more hemoglobin, then more O2 can bind, which will ultimately cause more PO2 to diffuse into the blood. Yeah, it's confusing just because there's a difference between when you're talking about the total amount of oxygen in the blood versus the PO2 in the blood. And the thing you need to just accept and know is that changing the amount of hemoglobin does not change PO2, it does change total oxygen. I thought he had a picture there, yeah. Well, no, it's not that good. But I guess if I could draw on here, I would say over in this area, the blood would be at 40 because it just passed the working tissue. 40, 40, 40, 40, 40. And then here, 100 stays 100 all the way through to here. When you're looking at the lungs and blood change, if you change the atmosphere somehow, it will just change both the PO2 of the lungs and the blood in the same amount, but it won't drop them the same number of PO2, correct? Like they will both drop by 20, but they won't both drop 250 specifically. No, I would say they would drop to 50 specifically. So what I'm saying is if you have 160 in the atmosphere, and then you have 100 in the lungs, then the blood will be 100 for PO2. So if you change it to where it's 50 in the lungs, then it will become 50 in the blood. And if you increase and decrease hemoglobin, you will not change what these are. You will change the total amount of oxygen going in, but not the PO2. Which I think he kind of, yeah, there, this slide here. Oxygen that is bound to hemoglobin does not contribute to PO2. So that's kind of like he says here, it says hemoglobin binds to oxygen, and when oxygen is bound to hemoglobin, it does not contribute to the PO2. This is how hemoglobin can store so much oxygen. So if it was contributing to the PO2, then less oxygen molecules would go into the blood. But because they're constantly being kind of taken up by the hemoglobin, then more and more can flux in. Okay, could you explain again why changing PO2 levels in the lungs changes PO2 in the atmosphere? Doesn't PO2 in the atmosphere stay constant? Yeah, it's the other way around. It's changing PO2 in the atmosphere changes the lung PO2, not the opposite. And PO2 in the atmosphere does stay constant as long as you're staying in the same place. If you go to different elevations, then it will change. How can you determine the level of influence on change of atmosphere PO2 on lung PO2? It's just direct. So if you go up an elevation and decrease your atmosphere PO2, you're going to decrease your lung PO2. If you, I don't know, artificially blast the atmosphere with more oxygen somehow, then that's going to increase the lung PO2. It's just a direct relationship. What's not direct is the effect that's going to have on oxygen delivery because of the hemoglobin graph. And it seems like, you're really emphasizing that point. Maybe because it's important, I don't know. But if they are the same number, so I guess you're referring to like the 50, how does diffusion occur from the lungs to the blood? That's a great question. So I should expand on that. Let's say you have lungs and let's just go back to the normal one. The concentration is 100 millimeters per oxygen. There is blood coming from the working tissue and then blood leaving the lungs. From the working tissue, it's about 40. But by the time it leaves the lungs, it's 100. Or in the other case, it would be 50 and 50, right? So yeah, you're saying how would it flux in if it's already if it's equilibrated, if it's at the same one? It wouldn't if what was coming in was 100. But because what's coming in is 40, that's how you get flux in. So the blood, when it first contacts the lungs, there is a gradient, but very quickly that gradient disappears to 0 for the blood leaving the lungs. So gradient is here, but not here. So if you had like the lungs, I don't know, try to put oxygen back in the blood of the arteries that were already at 100, yes, it wouldn't work. But it's because it's receiving blood that's 40 and then turning it into 100. Since more PO2 is fluxing into the blood, doesn't that mean it is changing? I'm sorry, this is so confusing. It is so confusing. I agree. I'm not sure if what I just said answered. It is changing from like, again, if I redraw this, I don't know if this drawing makes sense to y'all. It would be 40 going in, the lungs is 100. So now there is oxygen fluxing in and it does change to be 100. So you could think like within, let's say, milliseconds, you would see within the lungs it go from 40 to 41 to 42 to 43. And it's fluxing, fluxing, fluxing in from the lungs. And it goes from 40 to 100. So yes, it does change. It's just, we typically don't show this because it happens so fast. That's why we say it just comes into equilibrium. But it's also like not stagnant. So it doesn't just reach 100 and then stop there and then there's no more flow, because this movement is constantly happening. So even though we have this 40 blood come in and then oxygen's going to flow in, the increased pressure blood, the one that's gone from 40 to 41 to 42, 43, etc. to 100, is now leaving. It's now way over here. Now we have more 40 coming in. So we have, because we have this constant flow, we're going to have this constant flow of oxygen from the lungs, because it's always giving oxygen to that 40 blood, getting it to 100, and then that 100 is leaving. I don't know if that makes sense. This one says, then how does hemoglobin not affect PO2? So because the PO2 is just kind of a reflection of whatever the lungs is, it doesn't really matter what's going on with the hemoglobin. So whatever the lungs PO2 is, that's what's going to, the blood is going to get to. It has nothing to do with what the hemoglobin is doing. Would the working tissue PO2 be staying the same as it equilibrates with the blood PO2? So the PO2 of the oxygenated blood is 100, and the working tissue is 40. The deoxygenated blood would then be 40. The working tissue would still be 40. Yeah, the working tissue determines what the PO2 of the blood is that is going back up to the lungs. So it affects the PO2 in the blood, but not the PO2 in the lungs. What is it? Yeah, question?
Hi. So the blood that's going to the working tissue has a lower PO2 than the lungs, right?
The blood that's going to the working tissue here
Yeah,
is 100. So it's the exact same.
it's the exact same.
And then it goes to the working tissue. Then it equilibrates with the working tissue, becomes 40, then goes back. Now we have that gradient. It'll come back in, it'll become 100 and keep going.
Okay, gotcha.
Okay, so hemoglobin affects the PO2 in the blood, but not the PO2 in the lungs. Hemoglobin does not affect the PO2. So here's the slide. He says oxygen that's bound to hemoglobin does not contribute to PO2. So it does not affect the PO2 in the lungs or the blood. The only thing it does affect is the total amount of oxygen. So you can think that, okay, let's imagine that hemoglobin does affect PO2. If that were the case, so let me draw. Here's my blood. And I'm going to say all of these little dots are molecules of oxygen bound to hemoglobin. And these are just oxygen in the plasma. Now, if we have, let's say, in the lungs, this amount of oxygen. If let's go. Okay, if these black ones, these black oxygen molecules that are bound to hemoglobin contributed to the overall PO2, then the overall PO2 of the blood would be higher than that of the lungs, right? There would be a higher concentration of oxygen here than there was in the lungs. And you would actually get oxygen moving in the wrong direction from high concentration to low concentration. That would be bad. But what we see is oxygen that is bound up to hemoglobin in the red blood cells. They're all in there, in the red blood cells. They don't contribute to PO2. Only these guys do. Because of that, now we have a higher concentration in the lungs and the blood, and we get movement from the lungs to the blood. If these did contribute to the PO2, we wouldn't get the situation of getting a bunch more oxygen into the blood. So what we can do is now move these molecules into the blood, but instead of just contributing to the PO2 and making this bigger and bigger and bigger, as we move an oxygen molecule into the blood, those don't contribute to the PO2, they actually get taken up and become hemoglobin, hemoglobin bound. So those become black, and the black ones don't contribute to the PO2. So we always get this nice gradient between the lungs and the blood because those molecules aren't contributing to the PO2. I don't know if that helps. It helps my brain, but you can keep asking if it doesn't make sense. Did you say that decreasing the concentration of oxygen in the lungs decreases the flux rate of oxygen to the blood? Yeah, that's just kind of basic flux. So if you decrease the concentration here, then you're decreasing the total gradient, right? You want it to be high in the lungs, low in the blood, and then you can get flow. So it's typically 100 in the lungs and then 40 in the blood. But very quickly, as soon as it gets to the lungs, it becomes 100. But yes, it has to initially be lower to get movement. Yeah, question?
Oh, hello. So if all the blood that's coming to, or all the oxygen that's coming to the blood goes to the hemoglobin, doesn't that mean there's a lower PO2 in the blood? Or does the blood just naturally have more oxygen floating around? Because hemoglobin doesn't contribute to PO2, but you said all the oxygen from the lungs binds to hemoglobin.
Well, technically 98% does.
Okay,
Yes.
so that 2% is the same as the lungs.
Yes. Yeah.
Okay. So
And
there's just
initially when it comes in, it's technically yes, less, but then it turns into.
So
Yeah.
not all the oxygen binds to hemoglobin.
Yeah, not all of it does.
Okay.
Because this is totally a representation of non-bound oxygen. And if all of a sudden we somehow magically made all of the hemoglobin release all of its oxygen into the blood, this would become huge. And if that was true, then we wouldn't get flux from the lungs. So it's almost like hemoglobin is taking in a bunch of oxygen and hiding it and being like, oh, this doesn't really exist. It's here, but like the gradient can't see it. So the gradient's going to keep coming because I'm hiding this oxygen. It's not really here. So keep fluxing in towards me.
I have a question.
Yeah.
So the example number of the 40 means the partial pressure of like blood.
Yes.
So that number equilibrates to be 100 to get the same partial pressure, or
Yes.
other? Oh, okay. Thank you.
Did you say that decreasing concentration of wait, I think I already answered that. Wait, is the 100 down arrow that you just drew from the blood? Pressure equilibriation. It's confusing. Yes, it is so confusing. I don't know if you're referring to this, but this is the lungs, and then this is the blood. And so coming in, the blood is 40, and then coming out of the lungs, it's 100. And yes, it comes in towards the 40 and then very quickly turns it into 100. And so a big important point, this is reminding me of something else that's really confusing to people that you should know, and it's just confusing, is that let's say we have some lungs over here that have 100 as their concentration, some lungs over here that have 200 as their concentration somehow magically. And another person that has 100. And this first person is just normal. They have blood coming in from the working tissue, that's 40. This person over here is working out a bunch. And so they're actually having blood coming in, that's 20. And then over here, this person who has lungs at 200 are just normal. So they have blood coming in, that's 40. What is going to be the effect of oxygen delivery in each of those people? So how is oxygen delivery going to differ? So in this person, they're going to have blood coming from the lungs that is 100. And that's perfectly fine. That's great, right? Why? Because if you look at the hemoglobin saturation curve, when PO2 is at 100, we're very saturated. this person has a ton of oxygen. All right. What about this person over here? This person is going to have a blood PO2 of 200. And you might think, wow, that person has so much more oxygen, right? It's great. No, they don't. Why? Because the oxygen, the hemoglobin curve, right? The hemoglobin curve looks like this, and it's saturated at 100. If you move to 200, there's the same amount of oxygen on your hemoglobin. And 98% of the oxygen in your blood is on hemoglobin. So if it's the same here, there's no difference. So these two people, no different in how much oxygen they're able to deliver. Okay, what about this person? They're starting with 20. What is the amount of blood they're going to, the amount of oxygen they're going to be able to deliver? Again, it's just 100. It's just 100 because this number has nothing to do with this number. This number is just a reflection of what's going on in the lungs. So if it's 200, then it's 200. It's 100, it's 100. It doesn't matter what's coming in. And you might be like, what? What are you talking about? Flux? What do you mean? There's a larger gradient in this person. This person has a gradient of 80, and this person has a gradient of 60. So there's more flux, right? Yes, there is, but because it equilibrates so fast, even if the flux is slower here, it still gets the blood to beat 100. It's not so slow to where it doesn't end up at 100. That's super confusing for people, but it is true. So what you should remember is whatever gets to your body is whatever the lungs is. And if you put that number into your hemoglobin graph, it doesn't matter if it's 100 or 200 if you're saturated. Now, it does matter if your lungs is down at like 40 or something really low and then you're not very saturated, then it does matter. But as long as you're up in this region, you're good. And this number has nothing to do with this number. Yeah, question?
Yeah, so between the 100 and 200, there's no difference in hemoglobin.
Yes.
So the y-axis is, okay, the y-axis is SpO2, right? Or no, hemoglobin, right? The y-axis is
Hemoglobin saturation.
hemoglobin saturation. So what causes the 200 level? Like if there's no difference, what does it mean?
So 200 would be like maybe someone was getting like oxygen supplementation. They were
okay.
adding oxygen somehow.
Okay. And that just has no difference in function or anything.
Yeah. So you would think that if you were walking around and you supplemented your oxygen, you'd be better off, but not necessarily. No.
Okay, thank you.
You're welcome. Okay, did you say that decreasing the concentration of oxygen in the lung? Oh wait, I already did that. These numbers are all referring to partial pressures. Yes, yeah. All right, any other questions? Okay. Then yeah, if y'all have more questions, I'll keep an eye on Piazza to try to help. Oh, wait. Oh, I didn't see these. Sorry. If equilibration happens so quickly, how does oxygen, sorry. How does oxygen keep fluxing through the body? So even though it turns the blood's concentration very quickly to whatever it is, that blood doesn't just stay there. It leaves and goes to your body. So there's always that 40 blood coming in and continuing to get oxygen to flux from the lungs, because the 40 blood's continuously coming in. And it very quickly changes, but then that changed blood is gone. Will we have enough time to finish the test without needing to rush too much? The test feels pretty long to me, but it seems like, you know, he doesn't know what's going to be normal for y'all. So I would just take it, you know, and if everyone is still not finished by the end, I think he's going to take that into account, you know, hopefully. PO2 40 to 100, 100 to 100 in blood happens because the speed of flux is too fast, or it's very fast. Yeah, it gets all the way up to 100 because yes, the flux happens very fast. All right, well, I guess I will end the Zoom, and yeah, just post on Piazza if you have more questions.
Thank you.
Of course,
Thank you.
of course.